So when learning about stoichiometric conversions for the first time, many students try to do something in one step, and their teacher will tell them to do it in 3 steps. They'll try to directly turn grams of a chemical into grams of another chemical without converting into moles. And this is going to be a video about that process, stoichiometric conversions and the gram ratio. So when I've taught you to do stoichiometric conversions, what I've suggested is that you take any grams representation of a chemical and you turn it into a molar representation using the molar mass. Then you use the mole ratio from the chemical equation to figure out the associated number of chemical Y moles. Then you take the molar mass of the new chemical to change it back. That's how you do a grams to grams conversion problem. But why do we do it this way? Why do we need to shuffle into moles and back out? This feels kind of unnecessary. Why can't we directly convert using grams? Why isn't there some sort of gram ratio process where we just take grams of chemical X and then directly, in one step, flip it to Y? Then you wouldn't have to go into moles and back out all the time. Seems like it would cut out a lot of extra work. Well, the bad answer is because you don't have the gram ratio in the problem. The only things you're given are a periodic table and a chemical equation. And the periodic table will give you the molar masses. The equation will give you the mole ratios, but nothing will give you a gram ratio, so you just don't have the tools. If you don't have it, you can't use it, but that's the bad answer. The good answer is that you actually can do this. You can use a gram ratio. You just have to make it yourself. Let me show you how. So the chemical reaction, it gives you a molar relationship, not a gram relationship. For example, the mole ratio in this problem between aluminum and O2 would be, well, you look at the coefficient for aluminum, that tells you how many moles of aluminum you have. Then you look at the coefficient for oxygen, tells you how many moles of oxygen you have. It's 4 moles of aluminum to 3 moles of oxygen. And if I wanted a gram ratio, I could just figure out how much mass was in each of these quantities, right? So 1 mole of aluminum is about 27 grams. So 4 moles of aluminum, 4 times 27 is 108. I can also figure out the mass of the other element. 1 mole of O2 is about 32 grams. Now oxygen is like 16, but O2 is 2 oxygens, so you multiply it by 2. So 3 moles of O2, well, you multiply it by the molar mass, it's 96 grams. So I found the gram ratio. It wasn't that hard. You get it by taking the mole ratio and then multiplying each chemical by its molar mass. It says element, but maybe not element, maybe chemical, sorry. You can use this to solve problems. So for example, how many grams of aluminum do I need to react with 62 grams of oxygen, O2? Well, I need to multiply it by the gram ratio, but the equation gives me the mole ratio, so I'll multiply each chemical by its molar mass, and then there we go, that's the mole ratio. That's the gram ratio. So now that I have it, I can multiply this. 62 times 108 over 96 gives me 69.75, so that's the answer. Another one, how many grams of O2 do I need to make 90 grams of aluminum oxide? Well, I'm going to start with 90 grams of aluminum oxide, and I need to multiply it by a gram ratio, but I only have the mole ratio. So I'll take each chemical and multiply it by its molar mass to get the gram ratio, and now I can do this conversion without jumping into moles. 90 times 96 over 204 gives me 42.3529, which I'll just round to 42.35 grams of O2. So if we can use a gram ratio, why would we ever do it the 3-step way, going into moles and then out of moles? Why would I initially teach you to do 3 fractions instead of just 1? So the top is what we just did, where you use the gram ratio. This bottom is what I taught you before. You start with grams of the chemical, then you move into moles with the molar mass, then you use the mole ratio, then you move back with the new molar mass. So 1 step versus 3 steps. Why would I teach you a 3-step process when a 1-step process exists? Now the first reason is because, mathematically speaking, they're the same. I'll show you. Let me just reshuffle this around. You multiply a bunch of fractions, and you remember that they sort of combine together to form a big fraction. I'll rearrange it. And when you multiply by 1 mole on the top and 1 mole on the bottom, that doesn't matter. Multiplying by 1 doesn't change anything. Let me just do some shuffling to make this look the same. Bring this over, and then make the fraction smaller. Okay, boom. On the top, we had the gram ratio. On the bottom, I rearranged this 3-step stoichiometric process. And the numerator of both of them is the coefficient of y times its molar mass. And the denominator of both of them is the coefficient of x times its molar mass. So these are the same. But just because they're the same isn't a reason to teach you one over the other. The better reason is because it's conceptually cleaner to turn each individual step into one mathematical operation. There are a lot of different ways to do things in science, and the things that you're taught in an introductory course like this one are supposed to be generalizable techniques. Using equality facts to create conversion fractions is a technique that you can actually use in a ton of different places. It's called dimensional analysis, and it's extremely important in all branches of science. But using gram ratios to relate chemical quantities isn't really generally useful. You're going to use it in chemistry and nowhere else. It's not as versatile of a tool. The point of this lesson is actually just as much to teach you how to do dimensional analysis as it is to teach you about how to relate gram quantities of chemicals. Anyway, I hope this was helpful.